Welcome to solverfy.
Okay, so we're doing chapter 22, problem 47 here. And in this problem, we have a flat slab of non-conducting material with thickness 2d. I'm going to go back to black here, which is small compared to its height and breadth. Define the x-axis to be along the direction of the slab's thickness with the origin at the center of the slab. So that's what's shown as here. And if the slab carries a volume charge density of PE of x to be negative P naught for negative dx less than 0 and positive P naught for 0x less than d. Okay, so we now want to determine the electric field as a function of x in the regions outside the slab, in the left part or in the right part. Okay, so first of all, the electric field from a flat infinite slab is given by rho d over 2 epsilon. So this means we can take the total as E from the left plus E from the right, but this now becomes d over 2 epsilon naught over rho left plus rho right, and that's just d over 2 epsilon naught. Our rho on the left from the left slab is negative P naught plus P naught, and that's just 0. So outside of the slab, no matter where we are, there's going to be no charge because the electric field from an infinite slab does not depend on d. It does not depend on the distance away from the slab. It does depend on this d, the thickness, but does not depend on the distance away from the slab. So, but now for part B, we want to look at the electric field for x less than or equal to d, so in the right part of the slab. So to find this, we know we're going to need to use Gauss's law here, where we have E dot dA. So if we draw our Gaussian surface here to be a cylinder with cross-sectional area A, then we see that the electric field is going to be perpendicular to the surface at all points and parallel to the surface on all the curved parts of the cylinder. So if it's always perpendicular, we can decompose this integral to just being E dot dA or E times A. And this equals the charge enclosed over epsilon naught. So now we rewrited the electric field in the right slab is written as Q enclosed in the right slab over epsilon naught A. So now we've solved this problem, except we got to find what Q enclosed is. So Q enclosed is given as the volume charge density. So now we need to multiply this by the cross-sectional area of our Gaussian surface, which is A, and how thick this is. And that's going to be given by D minus X. Okay, so if this is our Q enclosed as a function of X, then we know that our ER as a function of X for the right side, then this is given as rho naught d minus x over epsilon naught. Awesome. That's it. So let's move on to part C here. I want to add a new page. Part C, we're going to be doing the same thing, but to the left side now. We're going to be doing the other region where x is less than 0 and greater than negative d. So now we have the same equation where our EA equals charge enclosed over epsilon naught, but now our charge enclosed is negative P naught d plus x times the area, cross-sectional area. And this is all over epsilon naught, so our A's cancel out, and we're left with an E of negative P naught d plus x all over epsilon naught. Awesome. Also, we know that this is in the left area, so this is pointing to the left, so we can rewrite this as a vector as negative P naught d plus x all over epsilon naught, and we know this is in the negative I direction. Awesome. So let's move back to part B because we didn't actually do the direction there. So in part B, this was what our magnitude as a function of x is. So let's write it as a vector. And this is now positive P naught d minus x over epsilon naught. And we know that the field is pointing to the left. So this has got to be a negative I. Awesome.